So now we're going to talk about relative error. So we talked about using the derivative to do a linear approximation. We then talked about using differentials to estimate the propagated error. And then now we're going to talk about the relative size of that propagated error. So usually the way this works is that you have some x, which is a measurement, and then you have delta x, which is the measurement error. Okay, and then you're going to have some value q, which you calculate using x. So in the previous example, what was the quantity that we were calculating? We were taking our measurement to calculate area. Area is the quantity. So then delta q is your propagated error. Okay, so delta q over q is what we call the relative error. Because you want to know basically how big your error is compared to the thing that you're calculating. We calculated in the previous example an area of 25 square centimeters, and it was off by 1 square centimeter. So that's maybe not that big, right? So remember, we had calculated our q. It was 25. We calculated 25 square centimeters, but the error was 1 square centimeter. So the relative error, delta q over q, is 1 over 25, which is a percentage, and what the hell is 1 over 25? 1 over 25 is 0.04, which is 4%. What that means is that, okay, so the area we're dealing with, we calculated it as 25 square centimeters. We think we're off by as much as 1 square centimeter. That means we're expecting to be off from the actual value by up to 4%. Oops, why is it not letting me type? In other words, we believe our calculated value to be off by up to 4%. Which is not that bad, actually, right? So the relative error gives you an idea of, given the size of the thing you're calculating and how much you think you might be off by, a decent idea in percentage terms as to the amount of error that you're dealing with. So let's do another example of this. Let's say that you're calculating volume. Okay, come on, let me write. There we go. Suppose you're calculating volume. If the accuracy of the measurement is, again, 0.1 centimeters, and the side of the cube is 5 centimeters, then we can ask ourselves, what is the relative error? Okay, so reading this, you're like, okay, cool, I measured x to be 5 centimeters. I was told that the accuracy of the measurement, delta x, was 0.1 centimeters. And now we're wondering about relative error for volume, basically. So you're like, okay, what I'm calculating here is volume. Volume is x cubed. So my propagated error is going to be delta v, because I'm working with volume. And that's going to approximately be equal to the derivative of v times delta x. Well, the derivative is 3x squared, and I measured 5, so you get 3 times 5 squared. 3 times 5 squared is going to be 75, right? So v prime is going to be 75. And then what was my delta x? My delta x was, so this is going to be centimeters squared, my bad. centimeters squared times delta x, which is 0.1 centimeters. So what does that end up being? 75 times 0.1 is 7.5 cubic centimeters. So according to this, I think that my volume could be off by as much as 7.5 cubic centimeters. Now what we want is the relative error. The relative error is going to be the amount that my error is over the actual volume. So you get 7.5 cubic centimeters divided by, now the volume is going to be 5 cubed, which is what, 125, right? 5 times 5 times 5 is 125. So what this is saying is, okay, we have calculated our volume as 125 cubic centimeters. We think that we could be off by as much as 7.5 cubic centimeters, which you plug all that in. That gives you 0.06. So we think that our propagated error means that given the fact that our measurement was only off by 0.1 centimeters, given the size of the thing that we're dealing with and that we're calculating volume, our volume could be off by as much as 6%. Now, this is sort of crazy because this tells you this is what the volume could be off by, relatively. Now, what was our measurement error? That's going to be delta x over x. Remember, our delta x was 0.1 centimeters. Our x was 5 centimeters. What is 0.1 over 5? That's 0.02, which is 2%. And this ends up being a very interesting thing that happens. The propagated error always gets bigger. So even though, relatively speaking, our measurement error was only off by 2%, right? We measured something at 5 centimeters, but it could be off by 0.1 centimeters. That's a 2% relative error for my measurement. Because we're calculating volume, that explodes or propagates up to an error of 6%. Most people would think that because your measurement error is 2%, that your area will only also be off by 2%. But it actually ends up getting bigger. And this is why measurement error is a big deal. So if you're an engineer and you're like measuring something in a building, like measuring the length of a side, and then you're using that side to calculate volume, your 2% measurement error all of a sudden explodes to a 6% volume calculation error, which is why this is like an important thing to be aware of, basically.